I'm going to be presenting the solutions we as QC Ware are building for different enterprises. And there are really two types of solutions, and I just realized I don't have the clicker on me, so if someone can give me the clicker, that would be great. So we have two types of solutions that we built for enterprises. The one type has to do with professional services engagement. So basically, we do pilot projects and proof of concepts for different enterprises. Thank you. And the other type has to do with our product. So what we're going to share in the next few slides now with in the professional services space are projects and successful collaborations we have completed with very large enterprises, and you can get an idea basically of what the industry leaders in the field are doing with a quantum computing partner, with QC Ware specifically. You can see the kinds of projects they're doing, the kind of use cases they're addressing, and what they're getting out of it. So this story, actually, we just announced this earlier today, and it just appeared in a Wall Street Journal article. We just announced our collaboration and our successful project with Goldman Sachs. What we did with Goldman was a project on understanding, basically, if we can figure out ways to speed up Monte Carlo simulation. So you might be familiar, some people have already mentioned it in their previous slides, that Monte Carlo is actually used for derivative pricing, and it's really a computationally intensive process. And obviously, there's significant advantage if you can reduce the time it takes to actually complete that process and do it faster, do it with better, with more accuracy, and derive these pricing components that are really needed for a big market maker, an investment bank like Goldman, faster than the rest of the market, really. It will potentially provide insights that are really valuable. The other thing that was mentioned in the previous talks is that you have all these algorithms that cannot really run on near-term hardware. And it turns out these quantum speedups from Monte Carlo happen to suffer from this disadvantage. It's not that we can run these Monte Carlo simulations on quantum computers right away. They actually suffer from the errors that quantum computers introduce. So actually, the objective of the project was to figure out whether we can effectively bring that time frame closer, to actually make the algorithms work in a way that they can actually give us valuable solution, even in the presence of noise. So I'm not going to say much more. Obviously, I welcome you to read the Wall Street Journal article or the press release that we jointly released earlier today. What I do want to highlight is that Paul and several other key financial players are going to be speaking at an industry panel on Thursday, on the third day. So you can hear a lot more perspective on this project and other projects like that on finance and how the finance industry basically is looking to partners and essentially start building skills in quantum computing. So with that, I wanted to give a little bit more detail on another customer we just successfully completed. So this project was also completed a couple of months ago. Equinor is a state-owned Norwegian oil and gas company. It's primarily petroleum-based, but they do have assets in gas, renewables, and several offshore assets like the one you see in the picture. We completed a project that had to do with optimizing effectively the drill paths that the drills are taking as they're digging into the subterrane. So this is a use case that has to do with figuring essentially the optimal path. However, because of several considerations, several business considerations, like the fact that you cannot really turn in very sharp angles as you're drilling, makes it a kind of interesting problem, computationally intensive. So it's not just a simple shortest path problem. You have to avoid certain features, obviously in the subterranean, and you're obviously targeting other features in the subterranean. And so it becomes an interesting problem to actually figure that out. It's computationally intensive. And the objective of the project was to really understand whether quantum computing can actually do something to improve on those results, whether quantum computing at some point in the future, again, remember, we're not talking about immediate ROI in any of these cases. We're really exploring what is the time horizon to get to a production level application, and these projects have always the objective to accurately pinpoint what that time horizon looks like for each use case, and then see whether we can actually shorten that time horizon. And we had a very interesting collaboration. Unfortunately, Equinor couldn't make Q2B, so you can't really talk to them, but I'll be happy to take any questions offline for the rest of the conference. The other customer we'd like to discuss more detail about is Ison. Ison is a very large Japanese conglomerate. It's a Toyota affiliate, and what they do is design, manufacture, and distribute car parts. So they're mostly well known for powertrains, like the one you see in the picture here. I believe this is a 10-speed automatic hybrid powertrain, and they are number one in the manufacturing and distribution of powertrains by market share in the world. So it's a major player in the automotive industry. And the use case we're exploring, this, as I said, is an ongoing project. The use case we're currently exploring with them has to do with effectively testing software, making sure that the software that controls basically these transmissions or powertrains works as expected, right? So this can be very complex code, and there are several classical approaches to actually do this code testing, but they take a lot of time. They actually take a significant amount of high-performance computing resources to actually feed all possible inputs into a model of the code, and then verify that what you're getting on the other side basically is the right answer. And in the case where the answer is not right, you have to go back, and the algorithm can tell you which subsystem, which part of the code, which subroutine actually failed, so you can concentrate your efforts to actually solving that part of the code. And obviously, so the project had this use case. The objective had to do with understanding how quantum computing can actually perform that a lot faster, and if it can be done a lot better. So one of the representatives from Ison, actually one of the team leaders that's very well informed and involved in this project, is actually going to be part of our automotive panel on Thursday, on the third day of the conference, and he's going to be talking with other automotive industry leaders that have active quantum computing projects, so you can also hear from the automotive leaders basically what they're doing with quantum computing, how they're approaching it, what are the initial use cases that they're dealing with. We've talked about our collaboration with Airbus before. We're really happy. We have a very extensive partnership with Airbus. We now have done multiple projects and multiple workshops. We've shared this use case in the past. This is a design verification use case, which is actually in parallel with the static code testing use case that we just presented, but this is more on the industrial side for a big company and an aerospace manufacturer like Airbus, where basically, again, you have to pass to a large, complicated system, several inputs, and you need to basically detect potential failures. And once you detect those failures, you need to determine which subsystem actually caused the issue so that the engineers can go back to the design phase, to the prototyping phase, and correct those issues at the subsystem level. And once again, I wanted to point out that this is a use case that Airbus is very much actively solving today with classical resources, with HPC resources, and they're spending a lot of time, they're spending a lot of cycles basically solving this problem, and they would like effectively to shorten that time horizon. This other use case we completed very recently. It has to do with flight path optimization. It's also similar to what we presented earlier on drill path optimization. What is the best route to take from A to B? But there's always some additional component. In this case, it has to do with minimizing time and fuel and avoiding weather patterns. And again, once you reach a certain point in your journey, following a certain route, that means that you might have certain options opening up and other options not being available. So it's a kind of a more complicated shortest path problem, as I mentioned earlier. I'm just going to share two more, again, in the context of providing you effectively more use cases that big industry leaders are addressing right now. So this one is with BMW. We did this project on quantum machine learning for autonomous vehicles. So the motivation comes from the fact that for autonomous vehicles, you need this massive amounts of data. You need to drive a lot of miles so that you can train these autonomous vehicles to basically know how to react to different driving situations. So the objective is really to figure out whether you can synthetically produce driving scenarios and data so that you don't have to actually drive all these miles, right? So there are certain models that they build that effectively synthetically generate driving scenarios, and the objective of this project was to see whether this QML approach could be used to effectively generate the synthetic data more efficiently. So that was the one use case. And the other use case comes from routing, once again, where there were basically two flavors to it. One had to do with essentially car fleet optimization and routing, where so you have to kind of solve this Uber problem, for lack of a better word, where you have multiple people that are hailing cabs or Ubers or whatever your fleet might be, and you need to minimize the distance driven and the waiting times and getting people basically to their destination. And the other problem that's still based on routing has to do with effectively moving the manufacturing, moving the robotic arms that are used in manufacturing in the assembly lines. In automotive assembly lines, they have to essentially complete a set of operations, so they have to move along a certain path, and the objective is to really optimize that path so that the arm can effectively most efficiently complete the tasks in the shortest amount of time. So with that, you have a pretty good sense, a pretty good idea of the different types of use cases we are exploring and we have explored in different industries. We have several other projects that are currently in flight. So we have projects with different energy companies, we have projects with additional oil and gas companies, and we also have material design projects that are in flight. And unfortunately, right now, we cannot name any names or mention additional details, but we hope to be able to make some announcements later next year. So what we have developed, and I want to share with you now, is a set of best practices. Because on the one hand, it's nice to see this. It's nice to see the end goal of partnering up with a quantum computing partner, a quantum computing expert. You see the use case that was addressed. You see that the project was completed, but how you get to that stage can seem a little bit insurmountable, especially when you're coming from one of these large enterprises that really has the R&D budget and the R&D scope to look at emerging technologies, right? And so we have developed over time a set of best practices, and I want to touch on each and every one very, very briefly, right? So the first thing that needs to be addressed is to why should you engage in quantum computing right now? That's really the most important thing. And as you've heard from earlier speakers today, the time frame for many of these applications could be 3 or 5 years away. So this slide was actually not meant to be read. I don't expect you to actually see what's there on the slide, but I'm happy to blow it up for you. If you, again, come and find me offline, I'm happy to actually go into detail as to why, how we answer this this why question, right? And I can give you a very brief description, which is basically, it doesn't have to do with ROI, right? So if you're looking for hard ROI, you're not going to get started on doing a quantum computing project. It has to do with readiness. It has to do with essentially building your own type of insurance against this potentially very, very disruptive technology, which is quantum computing. We always talk about the benefits that quantum computing will give us, and that is true. There are very, very significant benefits in the form of faster solutions or better solutions, but there's a very, very significant risk, which is that it will be a hugely disruptive technology that if you don't pay attention to it, your business might actually suffer. And that's the why, right? And again, I'm happy to expand and work on that more with you if you find me offline. The other thing we build is a roadmap, right? Essentially, again, when you come here, you see all the use cases, you talk to all the experts, you're kind of lost as to, okay, what happens next? Because you see these end states, you see these kind of final solutions with the different industry leaders, and so you're saying, okay, well, what's step number one, what's step number two, where do I get started? So we have actually, in fact, developed a roadmap. We've actually posted this online. You can go to the QCWare.com website and actually download this roadmap. It's actually a pretty simple roadmap that shares many similarities to what you would do if you're engaging in an AI or digital transformation or machine learning project. Actually, there is actually not a lot of fundamental differences between those type of projects. And the first thing actually on the roadmap, but I want to specifically highlight it, is starting with some education. So we found that to be paramount. Quantum computing is a significantly different field. There's a lot of things that have been written in the press. There's a lot of analyst reports that are great, but it still takes sitting down in a room for a few hours and really understanding what it can do, what it cannot do. And typically, what we've done is essentially put together this 2-day workshop for these large enterprises where we can bring in different technical experts, we can bring in managers from different business units and explain to them what can happen, what is possible, what is not possible, what are the different time frames. And at the end of this 2-day workshop, the most critical step is that we engage in this open-ended discovery process on specific use cases for the specific enterprise that we work with. And let me also add another bit of information here. If you're selecting a use case for quantum computing for an initial project, make sure it's something that's current. It's a use case that you're currently addressing in your current business. Make sure it's currently computationally tractable, and your data science team is actively working on it. We've talked to many players that somehow get the idea that quantum computing will solve these very intractable use cases, very futuristic use cases, but really there's no good way to get started on those, right? Remember, the objective of the projects is to build preparedness, to build readiness, and to do a lot of knowledge transfer and knowledge building. So it's important to build on something that already exists, and it's something that your team, your data science team, is already actively engaged in. And then the last thing is actually providing you with a template of what a typical project looks like, so there are no surprises, and we set very clear deliverables, very clear expectations. I mean, this is just good practice for professional services and consulting in general. Nothing new here, but it's worth mentioning. So this concludes the professional services part. So I'm now going to talk about our product that we have been building with the QC Ware team, and it's now available. We've actually released our QC Ware Forge product in September of 24 of September 2019, so a few months now, and it's currently in open beta. So you can go again online on the QCWare.com website or forge.qcware.com. You can sign up for it, and you can start seeing what it looks like right away, right this instant today, if you wish. So what does this product do? So let me take a couple of minutes here to talk about it. First of all, it's a cloud application It offers quantum computing as a service, and it addresses these 3 types of problems, and it allows you to execute algorithms for these 3 types of problems: binary optimization, chemistry simulation, and machine learning on these 2 types of back-ends: quantum hardware and quantum simulators. So now you might see that, and you might say, okay, well, this is great, but this is what everybody else in this conference is telling me that they can do, right? So how is this any different, right? And I don't blame you. There's a lot of, obviously, players in the space, and there's significant overlap among some. But let me actually clear it up a little bit and explain where we add value in a much more concrete way. So I'm going to start with the hardware layer here. So there are different hardware approaches that, like you've heard, there are quantum annealers, there's circuit-based or gate-based architectures, there are simulators, so obviously these are all offered by the different hardware players. And then what we typically see, or one way to represent it, is that there is this translation layer, or software development kits, or languages, whatever you might call it, that essentially allows experts to access that hardware layer. And what I say there in the text is that some of these might offer you basically a way to access multiple hardware architecture. Someone might be actually offering a translation service between different languages. So there could be many-to-many translations, or there could be all-to-all. I think effectively where we're going is that most of these will be all-to-all, right? And just to give a few examples in no particular order and in no preference, so you might say that, for example, IBM's offering Qiskit belongs to that layer, or is one of the things that it does, or Google's Circ offering, or open source library rather, and there are many others, right? So I'm not going to go ahead and mention all of them. So the other layer on top of that is this open source library layer, where people essentially are building binary optimization approaches, chemistry simulation approaches, machine learning approaches, right? And this is typically together with the other layer below, or sometimes separate, offer basically all these capabilities, all these different algorithms, effectively for an eventual user to use. Now, our users are typically sitting much higher, right? So the end user for all of this could be a data science professional, or a quantitative analyst, a quantitative chemist, but they're sitting up high somewhere. And we as QC Ware believe that there's another layer in between, and that's where we add the most value. And in that layer, what we do is effectively 2 very specific things. We allow the user to take large problems, and we decompose them so that they can fit into small hardware. And we offer speedups of the vanilla algorithmic implementations. And what it takes to essentially be able to do that takes an algorithmic team that designs new algorithms that can effectively say that for this particular problem and for this specific use case, we need to adapt the algorithm or change it in a certain way to get that speed up, or to get it to working on a different set or a smaller set of the problem. Now, our stack actually happens to contain many of the other layers as well, but the one we're proud of and the one we want to be known for and differentiated for is that layer up top. So with that, I also wanted to give a few examples of more tangible examples of where we've done those 2 things that I mentioned, the decomposition thing and the speed up thing, right? So this specific example, we built it using real data from a customer. Unfortunately, we cannot really say which customer it was. We were working on the D-Wave hardware. We're very happy with the D-Wave partnership. We have had a partnership with D-Wave for quite some time now, and they have a great product. And there's a lot of parameters on their hardware that can actually be optimized. And that's what our algorithmic team did. They took this great product from D-Wave, and they applied this new algorithm that they thought up, and putting them together basically gives you is Speedup an advantage over what you can do without having those two things working together. So actually, if you look at this graph, and if you think back to Adam's slide on scaling, then higher up in this graph is actually worse off, right? You're worse off because the y-axis has to do with time to solution, how fast you can get to a solution. So basically, the green line is this vanilla implementation without QC Ware, and the purple line is the implementation with QC Ware anneal offsets. That is an algorithm that we've written about, we've published, and we've now implemented here. So you can get that right now today if you access QC Ware Forge. So that's one thing, and that's on optimization. On chemistry simulation, we're very proud of this work. We actually very recently won a grant from the Department of Energy on this work. So what this is a very large bacteria molecule that absorbs light. That is what it is best at doing. And so the objective of this project was to actually try to find a way where we can simulate very large molecules. We're not talking about 5 or 10 atoms, we're talking about hundreds of atoms and thousands of electrons here. And what we did is, obviously, we cannot really fit that into a quantum computer as is, but what we figured out is the classical pre-processing, the classical decomposition of splitting up this very, very large system into smaller components, and then feeding that piecewise into a quantum computer that has only 18 qubits for this system that has thousands of electrons, and getting really the results that match what we expected, right? So we're getting basically the characteristics of this molecule that we were really after simulating, right? And again, this is research that has already been published. Stop by the booth, talk to Rob Parrish or anyone on the team about this work that we're doing. And again, this is something that we have implemented on our current QC Ware Forge platform. And finally, we're doing some of the things that Iordanis talked about earlier in his talk, where we take quantum machine learning algorithms with provable speedups, and we're putting them, again, into the platform to allow people to experiment really with these quantum machine learning algorithms. In this case, we're doing supervised classification. So if you have a set of data, A through E, each record has several different parameters, and then for each of these records, you have a certain label that you know is given, right, as part of the input data set. And so the objective is for a new data record or object to figure out the right label for that. And for that, if you were to do it in a classical way, you would need to basically spend 1 billion steps to get to that answer. Well, you spend 1 billion steps training that model. Actually, the point where you just take the label for X is a very simple operation, or simpler operation. And on the quantum step, you only need 1 million steps to do the same thing, right? And again, this implementation is available on QC Ware Forge today. So that's the differentiation. That's what's different. So for those of you that haven't seen it, this is a very simple screenshot. It's a Python notebook. It's a hosted Python notebook solution. So any of your data scientists should feel right at home, essentially using the solution and coding up in Python. And what you purchase in order to be able to use these solutions, to use these algorithms, is you purchase this quantum computing time metric. And what happens is that when you expend these QCT credits, you expend them on quantum simulators. You get charged at 1% rate. So basically, if you use 60 minutes of simulator time, you only consume 0.6 minutes of this QCT resource. When you're using it on quantum hardware, you actually do a 1-to-1. And then there will be some active seat usage for your users. This is the current back-end picture and the current back-ends that we're connected to. So gray, the ones that in gray are the ones we're still currently negotiating with our hardware partners. The ones in blue are the ones that are currently active. So please sign up today. You can get 30 days effectively for a trial and see how it's working out for you, and you basically get 1 minute of this QCT resource to try things out and see how you like the service. And with that, I'd like to thank you for listening in, and I'll take any questions.